Hello and welcome to the solution guide for Hysteria by myself, the pedaling pianist. I have spent hours and hours over the last few months trying to get this absolutely perfect, and honestly it's turned out better than I could ever have hoped for, so I'm delighted to have finally got it done. Now, as with any of these solution guide videos, I will honestly try my best to keep it fairly concise, but I do want to make sure that every explanation is sufficiently thorough, which probably means for a puzzle as difficult as this one, that the video, as you can probably tell, is going to end up being very long. Unfortunately, I just don't have the time to do lots of post-production and editing all of the inevitable hesitations and repetitions out of the video, so you will just have to bear with me. But you do have my full permission to go into those YouTube playback settings and just speed me up a little bit. I won't be remotely offended. In fact, I highly encourage it. Anyway, the rules are fairly short. We have chaos construction, but with a toroidal grid. What that means is we need to draw 9 non-overlapping, orthogonally connected 9-cell regions. But because the grid is a torus, orthogonally connected can mean a few wild things. Usually orthogonally connected just means 2 cells that share an edge. But in this world, these 2 cells share an edge because the grid is considered to kind of wrap around behind itself. Similarly, these 2 cells share an edge because it wraps around itself around the top as well. So in theory, we could make a region that does something like this. And on first glance, that does not look orthogonally connected at all. But of course, this is connected to here, which is connected up to here, and this connects down to here. So every cell in this region is orthogonally connected to at least one other cell in the region because the grid is a torus. Anyway, once we've done that and we've found our regions, it's just irregular Sudoku. So we need to place the digits 1 to 9 once each into every row, column and region. Some region borders have already been given. The grey lines are regionometers. So region borders divide lines into line segments. On each line, the sum of each line segment must strictly ascend from one end to the other. So these are a little bit like region sums lines in the sense that, well, on a region sums line, each line segment must have exactly the same sum, but here we're told that we might have a line segment summing to 3, and then 5, and then 9, and 14, and 32, and then 46, or something like that. Those values are very broken for a lot of reasons, but that's the kind of idea. It's increasing from one end to the other. Alright, those are the rules. The break-in is all to do with this long line going around the perimeter of the grid. Now, in any 9x9 Sudoku, it's possible to approximate the sum of all of the digits around the perimeter of the grid. This is going to be a set of the digits 1 to 9, so it is going to sum to 45. Same with this row, that will sum to 45. So together, orange sums to 90. We can say exactly the same thing about blue, which sums to 90. It's 2 sets of the digits 1 to 9. So the perimeter of the grid sums to 180, except we've double counted these 4 corner cells. So actually the perimeter of the grid sums to 180 minus 1 copy, let's say the blue copy, of those 4 corner digits. It's worth noting that the absolute minimum that we can make the perimeter of the grid sum to, well, in order to achieve the minimum, we need to maximise the corner cells because we're taking them away from 180. So if we put, say, 2 9s and 2 8s into the corner cells, that sums to 34. 180 minus 34 is 146. So that's the absolute minimum that the perimeter can sum to. We can also work out that the maximum is 174, but that's not relevant for this particular puzzle. Just remember 146. Now, from the perspective of the regionometer, we don't know much about it. We don't even know which end is going to be the bulb or the tip, but whichever end it is, the tip is a maximum of 2 cells. whichever end it is. Let's say it's this end. So the highest value that we can give to two different digits is an 8 plus a 9, which sums to 17. And that's the highest possible line segment sum on the line. So in order to maximise the sum of all of the digits on the line, we would need to take every line segment we possibly can. So that's 17, 16, 15, 14, 13, all the way down to 1. And the triangular number for 17, i.e. all of those numbers summed together, is 153. So we have now our boundaries, our bounds for our limit bounds for the sum of all of the digits in the perimeter. It's a minimum of 146 and a maximum of 153. What that means is we have 7 degrees of freedom. So what those 7 degrees of freedom means from the perspective of the corner cells is that they must sum to at least 27, because we need 180 minus these corner cells to be at most 153. So the corner cells must be at least 27 to get down to that figure. From the perspective of the regionometer, we need to lose a maximum of 7's worth of value from our line segments. So what that means is that if we do skip any of these line segments, the line segments that we skip must be a maximum of 7 in total. So for example, if we included the line segments 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, 16, and 17, that sums to 145. It's the triangular number for 17 minus 8. And 145 is less than the absolute minimum that we can make the perimeter sum to just by normal Sudoku. So now that we know we must have all of the line segment sums that are 8 and above, if we skipped them we would be losing too many degrees of freedom. We know we must have a line segment summing to 17 and 16 and 15 and 14 and so on all the way down to 8. That means we can tell which end is the tip. If we tried to make this the tip of the regionometer, we can make it 17 by putting an 8 and a 9 in there, but these two cells would then become a maximum of 6 and 7, and we need them to sum to 16, but that only sums to a maximum of 13. So instead, the tip of the regionometer is here, this sums to 17, and then we have some 16, 15, 14. We don't know exactly where they're going to go, but we do have those kind of going down column 9. So already, honestly, I was quite proud of finding this break-in. It's quite a cool break-in, and it's already pretty good. But it's this next step where, when I discovered it, I just had my mind blown, and I just thought, okay, this needs to be seen by the Sudoku community. Honestly, this logical step is one of the main reasons that I continued to persist through an enormous amount of frustration to make sure this puzzle got published. Right, the bad news is that it's probably quite tempting for a lot of solvers to now look at the low end of the regionometer and start trying to fiddle around with skipping certain line segment sums, eating up degrees of freedom here and there and seeing which options work and which don't. And I think if you do enough work with that, you can quite clumsily get to the right answer, but it's quite fiddly and it's not particularly neat. Instead, it's much better to look at this end of the regionometer, because we do know that this is a line segment that sums to 17. We know that we need a 16, a 15, a 14, and so on. And the magical thing about 16, 15, and 14 is that they sum to 45. So I'm going to consider those 3 line segments as one group, the 16, 15 and 14, and we're going to make them blue. What we can't do is make them stretch all the way down to there, because if we said that our 16, 15, 14 line segments sum to went all the way down to the bottom of column 9, we're saying that this sums to 45, but we know that the column sums to 45. And so that would mean that this digit would have to be 0. So actually we need to take some blue away. We don't know how much, but there are going to be some spare cells at the bottom of the column. Let's say it's 2. I'm going to highlight the column in orange because we know that also sums to 45. And so blue and orange are now equal. We don't know how far blue stretches, but wherever blue stretches down to, blue and orange are now equal. If we delete all of the cells in common, then blue and orange must still be equal. Blue equals orange. Why is this important? Well, because it puts a limit on the value that we can put in this corner cell. Now, if our 16, 15, 14 group stretches all the way down to here, then what this means is that orange equals blue. They're just the same digit. If it only stretches down to here, then what we're saying is that this corner cell is part of a group of cells that sums to blue, and therefore these will all necessarily be less than blue. And what that means is that the corner cell is less than or equal to blue. It cannot be bigger than blue. Why is that important? It's because we can now have a look at these three corner cells, but instead of looking at that cell in the bottom right of the grid, I'm actually going to look at this cell instead, because that blue cell represents a theoretical maximum limit for this bottom corner cell. So what's the most that we can put into these three cells, and therefore what's the most that we can put into these three corner cells? Well, they're all in the same row as each other, and also an 8-9 pair, so the maximum is 5, 6 and 7, which sums to 18. If we add a 9 over here, that sums to 27. And remember, we said that the four corner cells altogether must sum to at least 27. Well, we've now just proven that they sum to at most 27, so they must sum to exactly 27. We've eaten up all of our degrees of freedom, and the perimeter now sums to exactly 180 minus 27, which is 153. What that also tells us, because we have no degrees of freedom to play with, this corner cell cannot be part of multiple digits that sums to blue, because it can't be less than blue, it has to be equal to blue. So actually we can draw that, and that enables us to make this a region border, because we know that the 16, 15, 14 group goes all the way down to here. But far more importantly, and I'm going to get rid of these colours, what this means, now that we know that the perimeter sums to 153, we know we must have every single region line segment sum from 1 all the way up to 17. We can't skip any of them. We just don't have that wriggle room. So we need the first line segment to sum to 1, and the only way to do that is with a 1 on its own, so we can draw this region border in. Then we need a 2, then we need a 3, which can't be a 1-2 pair because we've already used 1 and 2, so that's another region border. Then this is on its own and it needs to be a 4. Then this needs to sum to 5. Well, it's not going to be 6 and minus 1 or anything like that. So we can draw this region border in, and suddenly the entire puzzle has blown up. I was just absolutely, in love with that logical step. It was, and particularly the reward that you get from it is just enormous. So we can take 5 out of those. We said, didn't we, that these two cells have to be the same. This is not going to be less than that. It has to be identical. So that is going to be a 6 or 7 as well. Now, after the 5, and by the way, I should say as well, just a setting insight. When I discovered that we had to draw these two region borders in, I was a little bit disappointed because it meant that I couldn't use standard chaos construction anymore. It was broken. The puzzle was broken. And then I had the idea to make the grid toroidal. So honestly, if I didn't have to make it toroidal, if I could have made it work without a toroidal grid, then I would have done. But actually, I'm quite glad that I did make it a torus, because there's some interesting logic that comes from that. Right, anyway, after the 5, we have a 6, 7, 8, 9, and 10. And the cool thing about 5 plus 6 plus 7 plus 8 plus 9 plus 10 is that that also sums to 45, exactly. So 5, 6, 7, 8, 9 and 10 must be entirely contained within column 1. That must be a region border. This must be part of a 10 sum. The only way that can work is if that's a 1 and we draw a region border just here. Along the bottom we must have, well, we know what this is. This is the 16, 15, 14 group. So let's actually work from the top here. We need this to sum to 16, this line segment. We've already got 13, we need 3 more, and it can't just be the digit 3 because of this given 3, so it must be a 1-2 pair, and that's a region border. The 15 can't be 2 cells summing to 15, because it can't be 6 and 9 or 7 and 8. The only 2 options because of the 6-7 pair. So it must be at least 3 cells, and it can't be 4 cells because that would force this to be a 1 cell line segment summing to 14. So we can make that a region border. That's 3 cells summing to 15, 2 cells summing to 14. That can only be 6 and 8 or 5 and 9, and it's not 6 and 8 because of the 6-7 pair. It's 5 and 9, and we know the order because of the given 5. So that's 5 and 9, and we can place 3, 4 and 8 into the rest of there. We can now do a few more region borders. Well, actually, before we do, let's just take a note of this cell. It's part of the line segment summing to 6, so it's either a 6 on its own, or it's a 2-4 pair. It can't be 1 and 5, and it can't be 1, 2 and 3, because of the 1 in the column. Now, whether this is 2 and 4 or a 6 on its own, it will either have a 2 or a 6 in the region, so it can't join up with this region over here, which already has a 2 and a 6. These regions can't join up together because we can't have 2 9s in the same region. Any other quick borders I can do now? No, I don't think so yet. But yes, all of that logic was just from the line around the perimeter and a few given region borders and digits. So yes, that's the break-in. Now we can move on to these wiggly regionometers. Let's start with this left one. Now we know that these are in the same region and these are in different regions, so these must be in different regions. So this is a line segment that sums to 1, so there's no way this can possibly be the tip of the regionometer. It must be the bulb. I feel safe in doing something like that. Should we make it a darker grey actually? No, I'll keep it as a light grey. I don't want it to be too intrusive. I didn't do that over here because if we made that the bulb of the perimeter regionometer, then we might mistake that for also being the bulb of the other 2 regionometers, so I'm going to leave that one off. But this one I think we can do safely. What that means is that this must be the tip of this left wiggly regionometer, and it can't just be a 1 on its own again. That will just break in all sorts of ways. So these must be part of the same region. Let's make it yellow. And because we know that yellow can't be the 2 because of this region border here, we can draw a region border just here. And we can give the 2 a different colour. Let's give it pink. Now, let's have a closer think about this row 9. We need these 8 cells to have line segments that sum to 11, 12 and 13 in that order from left to right. And because of this given region border, it's going to be either 11 and 12 over here, or with 13 over here, or 11 over here with 12 and 13 over here. We can't make any of them single cell line segments, of course, because 11, 12 and 13 are not valid digits in the Sudoku. Now, we can now rule one of those options out. This cannot be 4 cells summing to 11 because the only way to do that is with 1, 2, 3 and 5, and we've now got a 2 in this pink region, so we can't make all of this the same pink region. So this must be 2 cells summing to 12. We can put a region border here, and this must be 4 cells summing to 13. If that's a 7, then these 3 sum to 6, which has to be 1, 2 and 3. If that's a 6, then these 3 sum to 7, which have to be 1, 2 and 4. Either way, we definitely have a 1 and 2 in there. Oh, I did miss some region borders that we can draw in earlier actually, because we know that this digit and this digit are the same, but we know, excuse me, that these are part of the same region, so we can actually draw this in as a region border. And we can draw this in actually as well, because of this given region border, we know that these are not part of the same region, and yet these two are, so those two must be different as well. Okay, we can also now draw in this. Ever since we discovered that there must be a 1 in this region, it can't share a region with another region that has a 1. Okay, this yellow cannot be the same as pink, and so we can draw this region border in. Now, this is going to be orange, because I decided it. Now, I should make a note at this point that with this kind of puzzle, you have to be very, very, very careful when you're assigning new colours to new regions, because right now, there's no particular reason why orange can't be the same as pink, for example, if they join up like this. I don't think there's any way it can be yellow, that's just stretching too far, or maybe it could be if it kind of no, that's still 10 cells. But yes, we could potentially make orange the same as pink. So we have two choices, really. Either we can be careful now, or we can be careful later. What I mean by that is either we can do a very kind of cautious bit of notation like that. So this is kind of either a new region or it's the same as pink, and just kind of make sure our notation is always very careful. Or we can be careful later by making sure that we never make any deductions that are based on the assumption that orange and pink must be different. So for example, if we got to this situation, we couldn't then say something like, well, now orange has to skirt around pink or anything like that. Because, yeah, so no deductions allowed that are based on assuming that orange and pink are different until we prove that they are. That's the approach that I'm going to take, which is a much easier approach to take when you actually know the solution. So, spoiler alert, orange and pink do actually end up being different. Anyway, let's have a closer look at orange. It can go and take this 5, but if it does, it then can't continue into this region because we've already got well, that would put 2 1s in the same region. So even if we do collect this 5, that's only 3 cells, so orange must escape. We can also draw this region border in, because we know whatever colour this region is. Let's be a little bit reckless and assign it a colour. This can be green. That one can't be orange or pink, because of these region borders just here, but it could be yellow if it stretches down here, something like that. So again, we do just need to be a little bit careful with that. Anyway, so before we move on actually, let's have a look at this right regionometer. There's one little bit of logic that we can do that's very similar to how we started to approach this left regionometer. Again, we've got a situation where these are in a different region and these are in the same region, so these must be in different regions. So this is a line segment that sums to 5. Can it possibly be the tip of the regionometer? And the answer is just clearly no. Hopefully that's obvious. We could make this maybe 2 cells that sum to 4. We can make this 2 cells that sum to 3, we can make this a 2, we can make this a 1, but then we've still got way too much regionometer left to fill and no values with which to fill it. So this is the bulb. Again, I'm going to, I'll put the light grey one in, so that is a light grey bulb, which means this needs to be the tip again. And again, it can't possibly just be a 1 on its own, so this must be part of yellow. Yellow must come out, by the way. Ever since we drew this region border in at the top, it had to come out. But even 4 isn't enough, because we need this region to be, well, certainly bigger than 5, but probably quite a lot bigger than 5. So that's going to be yellow as well. We know that yellow is not the same as this 8-9 line segment because of this region border just here. So this actually joins up with its friends at the bottom of the grid. And again, I think, yeah, red certainly can't be the same as any of the colours that we've already assigned. It can't reach green, it borders pink, and it borders yellow. It can't reach orange or anything like that. Okay, we can also make this red because we need this line segment to be bigger than 5, but that digit is smaller than 5, so we need an extra little bit of help. Okay, now let's return our attention to the left regionometer. These two cells sum to 11 because of the perimeter regionometer. They have two options of what they can be. They can't be 9 and 2, and they can't be 7 and 4 because of this. This is either 7, 3, 2, 1 or 6, 4, 2, 1. Either way, they must include either a 7 or a 4, so this can't be 7 and 4. So this is either 3 and 8 or 5 and 6. That's not a 3 because of that, and that is not an 8 because that can't be a 3. Right. At this point, I'm going to do a step that's not entirely necessary yet, but doing it now just speeds things up a little bit later. What I'm going to prove is that this must be part of a line segment that sums to at least 8, even if it's not 8 itself. It must be part of a line segment that sums to at least 8. Obviously, if this is 8, then it's at least 8. If this is 5, then we're making that a 6 to make this sum to 11. So 6, that line segment needs to be at least 7, and therefore this line segment, even though that's just a 5, we would need to add to it and make it at least 8. If we made this a 5, however, then this would be at least 6. This would have to be at least 7. Let's actually play this one out because it's a little bit more complicated, but again, it's worth doing. So that's, if we make that a 5, that has to be at least 6. This would be a 6, but the line segment would have to be at least 7, so we would need to extend it up to here, but because that can't be a 1, it's actually at least 8. So in all of those different iterations, this line segment ends up being at least 8. It's easier to see that it must be at least 7. And that's enough for the next few bits of logic, and then you can come back to it to prove that it's at least 8. But for now, we've proven that it's at least 8, and that's going to be good. Why is that good? Because now we can ask, can this be the extent of the line segment up here? Well, if it is, we can make it a maximum of 9 in here, so 10 in total. Then we could put a line segment summing to 9 just here. Remember, we're going down from this end to the bulb end. So we can make this 3 cells summing to 9, and then, well, we would need all of this to be a line segment summing to 8, because we know that's at least 8, and that's just nonsense. That's far too many cells summing to 8. So actually this can't stop here. Yellow must extend to here. Now that yellow extends to here, we can ask, where does this 3 join up to? It can't be yellow because we already have a 3 in yellow. So that given digit did kind of 3 things. It helped extend this region, it helped extend yellow, and it helped draw this region border here. So actually 3 joins up to green, and green now actually must escape, which means orange must escape, because orange, whilst it can take the 5 in this corner, still needs at least 8 more cells coming out from this bottom corner here. Right, the next question to ask, well, actually, let's just draw in one more region border here first, because we know that 4 can't be green from this. And actually, we can do a little bit more here. This is not 3, this is not 8, because, well, this can't be a 3-8 pair because we have a 3 in the region already. That 5-6 pair gives us a 7 here, which has to go with 1, 2, and 3, and this now must be a 4-8 pair. Right, the next question to ask is, where does this 4 join up to? This bit is a little bit fiddly. I'm actually going to ask that question from the perspective of this cell, because, well, the 4 must get out, so it must be part of this region. I'm going to hypothecate that this is not yellow. Let's call it grey instead. Now, can this be a single cell line segment? And the answer is no, because the maximum it could be is a 9, and then again, because we know this is at least 8, well, we've now got another line segment here that's not green, so this now needs to be at least 9, so we can't make that only 9. So grey would have to stretch into here, and now there's a problem completing this 6 line segment along the perimeter. If it's a 6 on its own, then we need to draw that region border in, which means that that means that it can't be grey because of this region border, and so we need to draw this region border in as well, and it becomes an isolated cell, one cell region. So that doesn't work. And if we made it a 2-4 pair, then it does join grey, but now there are 2 4s in grey. So it's a little bit of a fiddly step. It's very possible that there's an easier way of seeing that, because I'm not the best solver in the world. So possibly, if you're a better solver than I am, you can help me out and tell me an easier way to see that step. But for me, I think it's just about fair enough. And the conclusion is that this can't be not yellow, so it is yellow. Now, yellow has 8 cells. We've only got one more cell for yellow. So now we can ask the question, can this be a 2-4 pair? Well, if it is, it can't join yellow because, well, A, we've already got a 4 in yellow, and B, that would mean 10 cells in yellow. So if we made this a 2-4 pair, it's not yellow. This 1 and 2 is certainly not yellow. It can't reach all the way into there. That's way more than 9 cells. So we get an X-wing on 2s in these 2 rows, so we can't have any more 2s in here. And so where is yellow going to get a 2 from? Yellow must acquire a 2 from somewhere, but it simply can't in this world. So actually this is not a 2-4 pair, this is a 6. And we can draw that region border in from the perspective of the perimeter regionometer, and that tells us that this must be part of yellow. It must join up somehow, and that's how it does it. We can now draw this in, because yellow is complete. It's 9 cells. Now, let's do a little bit of law of leftovers. Where do 4 and 1 go in row 2? They can't repeat in yellow, so they must go here and here, and judging by our pencil marks, it looks like we need to put the 1 there and the 4 there. That is a 2. This 4, I'm going to be hesitant about colouring it just yet. Am I? I think we can prove that this is a new colour. I mean, it certainly can't reach red. It can't reach pink, and there's a 4 in pink anyway. There's no way it's going to reach green, there's no way it's going to reach orange, and we know it's not this region. Let's actually give this region a colour as well, because, yeah, again, this region can't reach red. It can't be the same as this region. It can't be the same as this region, that's more than 9 cells. It can't reach pink. Yeah, so this is a new region, so we'll award that a new colour. And this, again, is a new region. It can't join anything that we've already coloured. And it must come out. Blue and grey cannot be the same based on these region borders. I think we can say safely now that none of these regions can be the same. I think earlier we were worried about pink and orange being the same, but if they were... yeah, that is 9 cells, but it cuts off green, so that doesn't work. Okay, so now we can extend red a bit, because this is now a maximum of 13. If we make this a 9, then 9 plus 3 plus 1 equals 13. So, what would happen? Well, let's think about this from the perspective of 5s. Where is red going to get a 5 from? We only have 2 more cells to add to red. We've got 7 already. But we've already got a 5 in this row, which cannot belong to red because there's a region border here. We've got this 5, so probably red is going to end up taking that 5, but could it take a 5 from this row instead? The only way it could reach this row is if it went directly like that, and these would be the remaining digits in red, which are 4, 5 and 6. That sums to 15, plus a minimum of 1 is 16, and yet it needs to be lower than 13 for the regionometer to work. So that's nonsense, it's not going to do that. The 5 that it takes must be from this row, and so that must be red. But we can keep going with that, because even just doing this is a problem. If we made this the last 2 digits now in red, a 4-6 pair, that's at least, well, that is 10, plus at least 1 gets to 11. That's, again, a maximum of 13, so we would now need all of these to sum to 12 and be part of the same region, and that's nonsense. I've just realised I'm not sure I explained why grey couldn't be the same as this region, although it's not relevant anyway because we haven't yet assigned a colour to this region. But obviously they can't be the same because there's a 4 in both of them. Anyway, the point is that we can't make this all sum to 12. That's 6 different cells, which is nonsense. So this cannot be red. Red's final cell must come from here, and that gives us a 4-6 pair. And that actually completes red as well, doesn't it? So we can draw these region borders in. Right, let's return to blue, actually. Sorry, it's a very long and complicated solution path, so I'm trying my best to remember it in all the right orders as smoothly as I possibly can, and I've just remembered that there's a 7 there, so let's sort out this 6-7 pair. Anyway, this light blue section might take in this 5, we don't know yet, but even then that's still only 5 cells. It can't escape over here, so it must escape through here, so that must be part of light blue. We know that this is going to be a line segment that sums to 7 somehow, but it can't be a 7 on its own, and it can't include the digits 1 or 2, because we now know that it's going to be part of the blue line segment, the blue region, so actually it must be a 3-4 pair. And that leaves 2, 7 and 8 for the column. And we need to divide them in such a way that we get a line segment summing to 8 and then a line segment summing to 9. The only way to do that is with an 8 there and a 2-7 pair just there, which get split up like that. Let's draw in a few more region borders. A 3-4 pair cannot connect to a 3-4-8 triple. An 8 can't connect to a 3-4-8 triple because that would mean 2 8s. We can take this 8 out. We can draw this region border in because, well, we've got a region border here, so we know that this is not orange. Now, can this be a single cell line segment? And again, no. We know this is at least 8, so this needs to be bigger than 8. So we need to add an extra bit of line segment just there. Now this 8 needs to escape. I'm going to award this purple, but again we need to be very careful because there are some regions that it could and probably will end up being joining instead. Anyway, it's purple for now. Again, can this be a single cell line segment? No, because this is at least 8, this is at least 9, so this is at least 10, so we need at least 2 digits to make that happen. And now we have a problem. Because orange, in order to make orange escape, it can't join the 2-7, so even if we take this cell, that's 5 cells, maybe 6 there, we still need to escape through this little tunnel just here, and that means green needs to escape through this little tunnel, and now pink is isolated, it's only 3 cells. So that causes a problem. So purple can't be a new colour, it has to be orange. It can't be green, because again that isolates orange. It can't be pink because that isolates orange and green and forces them into too small a space. So it must actually be the same as orange. We now have 3 digits on this line segment. Can we have a 4th? If we have a 4th, then these 4 cells need to sum to something. Well, what do they sum to? They sum to a minimum of 2, 3, 4 and 5 because we already have a 1 in orange. That sums to 14, and yet we know that the maximum that these 2 cells can sum to, if we put a 4 here and a 9 here, is only 13. So this can't be part of orange, which means we can draw those region borders in. Orange needs to escape through here. We can draw that region border in because the 2-7 pair cannot be orange. And now what do we do? We can look at the green and pink regions which must escape through this little funnel here. So it's fairly clear to kind of visualise how they escape, or roughly how they escape anyway, but let's just do it in a completely logical way. Is there any way this is not pink? Well, if it's not pink, then pink escapes this way, and green gets shut off. So that is pink. This can't be something that isn't pink, otherwise it will cut pink off from itself. And now green must take this cell, because whether it goes via here or both, it must kind of use that little gap to escape. Pink must use that gap to escape. Green needs to keep going, even if it takes both of those. That's 4, 5, 6, 7, 8 cells. We need another one there. So let's draw in some region borders. Okay, now let's do a little bit of law of leftovers in column 2, specifically regarding the digits 1, 8 and 9. They cannot repeat in orange, and by our pencil marks they're not 5 or 6 and they're not 4, so this must be a 1, 8, 9 triple. This isn't 1, we already have a 1 in yellow, and this isn't 1, we already have a 1 in light blue. So that must be a 1. We can't have another 1 in light blue, so these region borders become valid. And now what can reach that 1? Actually, let's have a quick count of how many regions we've assigned at this point. Well, let's assign these a region first. Can it be anything that already exists? Can it reach pink? No, that's way too many cells. It can't be the same as grey, because there would be 2 4s in the region. And there's nothing else that looks even remotely realistic. So this is a new region. This one, can that join anything? Can it reach pink? No, again, that's way too many cells. Can it reach grey? Yes. However, that would isolate blue, because even if blue takes in this 2, 7 pair, that's only 5 cells, and we can't like wiggle to give blue enough room to expand, because that just makes grey far too big. So this cannot be part of grey. Let's assign it purple. So we now actually have 9 different regions. We've got 9 different colours, and we know these are all different. So which of those regions does this 1 belong to? Can it be green? No, green just can't reach. There's just way too many green cells there. Same with pink, it just can't reach. Blue also can't reach. That's 11 cells, I think. Yeah, 11 cells. Same with purple. It's going to be grey. It's the only option that allows us to take in that 1. Now grey has 8 cells. We've got 1 more cell to place in grey, and it must be a 2, because 2 can't go in any of those cells. So that allows us to do things like that, because if grey did extend there, we would need to put a 2 there, and we can't, because there's a 2 already in the column. Now, light blue must extend. Let's put it over here, which means we can draw this region border in as well. And now, let's return our attention to this cell. It can only be green. It can't escape and find anything else. It has to be green. Now these 2 cells have to be fairly low, because remember, this is a maximum of 13 if we make this a 9 and this a 4. So this needs to be a maximum of 12 in order to be less than 13. So this needs to be a maximum of 11. This digit cannot be 1, 3, 4, 5 or 6. So it's going to be 2, 7, 8 or 9. But if it's as high as 7, well, if it's 7 or higher, then that's 7 plus a minimum of 5 plus a minimum of 1. That gets us to 13 already. But we said that this had to be a maximum of 11. So that can't be 7 or higher. It must be 2. Now this digit can't be 2 or 3. It can't be 5. It can't be 6, because there's a 6 in the region. So now it's going to be 1, 4 or high. Again, if it's high, 7 or above, that's just too much. 7 plus 2 plus a minimum of 5 gets us to 14. That's too much, so it's 1 or 4. Now, we can actually determine which one of those it is by asking where does a 4 go in orange. It can't go in here because of this 4 just here, so it either goes there or we take in this cell and make it a 4. So one of those is a 4, which means that can't be a 4, so it's a 1. Now we can do a little bit of law of leftovers in comparing green and column 4. So 1, 2, 3, 5 and 6 cannot go in green. We've actually already accounted for the 2, and this is not 1, 3, 5 or 6, so these must all be 1, 3, 5 and 6. This is not 1, 3 or 6, so it's a 5, and we can take 5 out of those. That's not a 1, and this one, yeah, this one is not a 1 or 6, so it's a 3, so that makes that a 6 and that a 1. This 3 cannot join green because we've already got a 3 in green. So these region borders are valid, and now the only region this cell can join is pink. And 1, well again, we can do this because we've already got a 1 in light blue and we've already got a 1 in green. So now, which region is this 1 a part of? It can't reach purple. That is, well, that's 10 cells as a minimum, even if we go there as fast as we can. It's not going to be part of grey, yeah, everything else, well, it's not going to be part of pink, because we've already got 7 cells in pink, so that would make it 10, so it must be part of blue, but it can't go directly along this row, because that would cut off grey. We know we need an extra cell in grey, so we've got to do some wiggling. It's either going to do something like that, or maybe it does that wiggle over here, or that. So we're going to have that kind of wiggle. But the thing is, if we do something like that, that's 10 cells. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, that's 10 cells. So it can't do that. And for the same reason it can't do that, because again that's 10 cells. It must be this, because by using this as the kind of part of the bridge that we're forming, we're being a little bit more efficient, and that makes it only 9 cells. So that must be what it is. That then becomes our final grey cell, which is a 2. Let's catch up a little bit on region border drawing. Make it all nice and neat. Now, where does 2 go in blue? It must go there. And interestingly, well, actually, before we do that, let's just finish off some region building. Light blue has 8 cells, and its 9th cell will come from either this 5 or this square here. Orange has 8 cells, and its 9th cell will come from, again, either this 5 or this cell here. So this is kind of a blue-orange pair, which means it can't be green. That's actually something that we could have done earlier, which extends green out into here, and that makes building this blue region a little bit easier, but hey, it was still possible. Green is now complete. That's 9 cells in green, so we can corner that off. Pink now needs to continue to here. Pink needs 1 more cell. We've got 8 already. This cell can't be anything other than pink, so pink gets complete with that. And everything else must belong to purple, including the cheeky 2-7 over there. So that's all purple. Right, this is obviously a maximum of 9 because it's a single digit line segment. Now, so these need to be a maximum of 8, and yet they're a minimum of 8 because we can't repeat 2 in purple, and so these become a minimum of 1, 3 and 4, and that sums to exactly 8. So now, so the 4 can't go here, so the 4 does go in here, which means that can't be a 4, it's a 6, but we know that this must be a maximum of 7, because it needs to be less than 8. So that actually becomes the 1, that sorts out the 3 there, and this 1 does the 1, 4 pair. This 2 sorts out the 2 and the 3. This needs to be 6 and 8, and we know the order. We need 9 and 7 in here, and that 9 tells us the order. and we are cooking with gas. And this also needs to be a 9 because it needs to be bigger than 8. This, to complete the column, is a 5. Right, let's keep going. I think there's probably some normal Sudoku that I'm missing at this point. 3, I think? That's not a 3. Yes, one thing we can do is we can have a look at where 8 goes in light blue. It can't go in any of the... Sorry, no, it can't go in any of those, can't be the 5, and even if light blue takes this cell, it can't go there. So 8 definitely goes in there, so that's not an 8. Now the 3-4 pair gives us an 8 just here. These need to be 5, 6 and 7. We can't quite complete that. We can take a 5 out of here and a 6 out of here. This needs to be 5, 7, 8, 9. No, this is not quite doing everything I want it to do, is it? These cells, let's look at these ones. These will be a lot more fruitful. We need a 1 in them, and that needs to go there. We need a 5, which needs to go there, a 6, which needs to go there, and a 7, which needs to go there. These need to be 4, 7, 8, and 9. The 8 must go at the bottom, the 9 goes here, the 7 goes there, the 4 goes there. Yes. If in doubt, even on my own puzzle, I can probably do normal Sudoku to save the day. 5 and 5, put a 5 just there, and this 7, or the 6 just there, resolves the 6-7 pair. This 7 resolves the 7 and the 2. This now needs a 3 to complete the row. This needs 4, and, well, 4 does go here. And what am I missing? A 2, I think. And this needs a 5-6 pair. This 4 sorts out the 4 and the 3. This also makes this a 3 and a 4. I have a feeling that was resolved a long time ago, and I can't remember why, but never mind. If you found a slightly different solution path, I think that's completely fair enough. We can complete this column. We need 2 and 3, and that's resolved. This is an unresolved 8-9 pair. This is an unresolved 7-8-9 triple. This needs to be... well, again, this is all unresolved 7-8-9-age. That's going to be a 7, 8 or 9. It can't be... Well, sorry, not a 7. Yeah, this is just an 8-9 pair by the row. So we're now stuck. We've been left with a deadly pattern on 5s and 6s and a deadly pattern on 7s, 8s and 9s, except of course we're not stuck because we can have a closer look at, let's have a look at this regionometer. We've got 11 here, so we need this to be more than 11, so this can't be a 7 because that would be exactly 11, and that would make it a slow regionometer, which it is not. So that's a 7, that becomes a 7 just there, but that still hasn't resolved our 8-9 deadly pattern. We need to use this instead. So this is either 12 or 13, this is either 12 or 13, 5 plus 4 plus 3 is 12, 6 plus 4 plus 3 is 13. But we need this to be bigger than this, so this needs to be 12, this needs to be 13, and that's going to do everything for us. 5 and 6 get resolved, that becomes a 6, that becomes an 8. Before I resolve the digits, let's resolve the regions, because we now have a 5 in orange, so that is a valid region border, and the 5 connected up to blue in the end. So that's blue, that is part of orange, so we can draw this region border in. I'm just very quickly going to scan the edges of the grid. I've missed that region border and that region border. I think those are the only region borders I've missed. I think everything else is correct. So let's finish off with the digits. That's a 9, 8, 9, 8, 9 and 8. And I've gone wrong. What have I done wrong? Oh, I just typed that in incorrectly. Okay, there we go. That's the puzzle. Brilliant ending there. Yes, thank you very much for watching. If you did have a go, then I hope it went well. I hope you enjoyed it. Yeah, I'm very chuffed with how this has turned out, but let's not make the video any longer. Please like, comment, subscribe, all the usual stuff. Thanks for watching, and I'll see you again soon.